So, free radical addition. Free radical addition was discovered in 1933 by Morris, I'm not even going to try and say that, and Frank Mayo. And then this is an overview of the reaction. So you have your radical and your alkene and the double bond. The electrons from the double bond will attack the radical, the unpaired electron of the radical, and then it allows the radical to be added to the carbon in the alkene and the other electrons from the double bond of the alkene to go to be unpaired. And this is the addition product radical. So a little bit more about the reaction. So this was discovered because there were inconsistencies in organic reactions, and they found out that in the presence of peroxides and heat or light, that the addition pattern changes. So normally when alkenes react with, in this case, HBr, they give the Markovnikov regiochemistry. So the bromine, in this case, would add to the most substituted carbon in the alkene. However, when in the presence of peroxides and heat or light, the bromine in this case, adds to the least substituted carbon of the alkene to get the most stable radical. The hydrogen from the HBr adds to the most substituted carbon of the alkene. So you can see that here, that the bromine is adding to the carbon with the least substituted carbon, and the hydrogen adds to the most substituted. And this is called anti-Markovnikov addition, which is the regiochemistry in this reaction. And this leads to a multi-step mechanism, often called the peroxide effect. And here's just another example, like general example of it, but in a cyclic structure. So again, the bromine will add to the least substituted carbon in the alkene, and the hydrogen will add to the most substituted. And there's no stereochemistry in this reaction, so it adds 50-50 of both the anti and the syn and enantiomers. And so here's a few more examples. So this is the exact same one as before. Here's another one with a larger group attached to the carbon. So again, the bromine is adding to the least substituted and the hydrogen is the most substituted. And here it is again. Okay, so a real-life example of this reaction is in the synthesis of prostaglandins, which is a large class of molecules found in almost every tissue and fluid inside the body. And a number of pharmaceuticals are based on or derived from prostaglandins, including medicines that induce labor, control asthma, help treat congenital heart defects, and then there's many other examples as well. So here, this right here is just a specific example of arachidonic acid going through the mechanism and of free radicals addition all the way through the propagation step and termination steps to get prostaglandin. So yeah.
Okay, so for free radical addition, first you have your initiation step, and in this case, we're talking about adding HBr and peroxides to an alkene. So that's why you would use this to go from an alkene to alkane. So first in the initiation step, you're going to take your peroxides, which in this case was H2O2, and you're going to break that up from the bond, like just split it in the middle, so you can form two radicals. And then during this, you will use heat or light to catalyze the reaction, and then you will form hydroxyl radicals, which will be important in the next second part of initiation. So in the second part of initiation, you're going to use the hydroxyl radical you just made from the peroxides to break the bond between the H and the Br so that you can form water and the bromine radical. Um, so then you'll take the bromine radical into the next step for propagation. So for propagation, you're basically going to take the bromine radical and it's going to meet with the alkene bond in the middle, and it's going to break the alkene bond. And then the bromine is going to add to the less substituted part of the alkene. So in this case, that would be um, carbon 1. So as you can see in carbon 1, the bromine was added to form the radical shown in the brackets. Um, the radical form in the brackets is secondary, which means it's lower energy and it's more easily formed. Um, but yeah, that's why this type of reaction is anti-Markovnikov and adds to the least substituted, just because it's a faster reaction and it has lower energy. And so then once you have your secondary radical, most stable radical, you're going to go into the next step of propagation, and you're going to basically use the second HBr that you had, like a leftover, and you're going to, again, um, add that to your radical, and the bond is going to break between the H and the Br again, and the radical is going to meet with the bond, and it's going to take the hydrogen. It's going to pull the hydrogen off, and the bromine is going to form another radical on its own. So then you get the alkane that it shows right there with the bromine and the hydrogen both added, and then the bromine radical separate as like a byproduct. And then in the last stage of this reaction, it's called termination. So you're just going to take both of your radicals that you have left over from some previous steps, like step 2 and step 4 have a bromine, 2 bromine radicals left. You're just going to add together to form a bromine bond between the two to finish it off. So the overview of this is basically you took hydrogen, um, you took HBr and peroxides to break down an alkene to an alkane. So this is just one way you may do that. Also, one more thing to add with the overview of this. So through all these mechanistic steps, initiation, we break down the halogen. Two, in propagation, you're going to break down the pi bond, and then in termination, you're going to combine the two leftover radicals to finish off the reaction. But yeah, this is basically how you go from an alkene to an alkane through free radical addition.